I'm Dr. T and welcome to my office. So when I'm talking about mixtures, I do need to bring in a little bit of a caveat. Previously, I've kind of described them as being, any old ratio. And for some cases, that is true, especially when you're talking about miscible liquids. You can have ethanol and water, and you can make a mixture, and you'll have a solution of any ratio you would like. However, in order to get a mixture, there are certain solvent-solute pairs, actually most of them, in which you can only dissolve so much solute into the solvent. It's just not able to carry any more of it. And so when looking at these, it's helpful to understand what's going to affect these properties. Once you have dissolved as much solute as you can, then simply adding more solute will cause it to sink to the bottom and you get suspension or some other heterogeneous mixture instead of your homogeneous mixture that was your solution. Now, when you do this, you will get some of the atoms and molecules of your solute to precipitate out or to separate in one way or another, as well as some of the solute that you've added that hadn't dissolved going into solution. But the amount that comes out and the amount that goes in will be the same, and so there's no net dissolving taking place. Now, what affects these? Well, the first, of course, is what the chemicals are. So different chemicals are going to have different ratios in which they can dissolve each other. The other one is going to quite often be temperature, and this is heavily dependent, but it actually depends on what material you have. Temperature encourages things to be more disorderly. So the higher the temperature, the more disorder is going to be desired by the particles within your solution. This means that highly ordered things like solids tend to dissolve better once the temperature goes up. And of course, we've all seen this. Hot water dissolves things faster than cold water. And you can make a solution saturated by taking an unsaturated solution and cooling it down some so that, hey, it can no longer carry as much because the temperature is now lower. Likewise, a saturated solution heated up will become unsaturated because, hey, it's now hotter, you can dissolve more. Now, when it comes to gases, though, the opposite's going to be true. Gases in their gas phase are actually more disordered than when they are in the solution, so temperature tends to have the inverse effect on this, and thus raising the temperature of a solution where the solute is a gas is probably going to result in less solute in your solution. We actually see this very interestingly when it comes to fish. If you look at big fish, really big fish, these are typically going to be found in colder environments. So of course we're talking things like cod and tuna and gigantic fish. Those are found by the poles. Whereas if you go towards the equator where it's warmer, you see lots of fish, but they're little fish. This is in part because it's harder for the fish to breathe when they are in warmer water. Therefore, it's harder to have big fish. Don't get me wrong. Sunfish are huge. The fish can work around this issue. It is definitely something they have to take into account. The other issue when it comes to gases that doesn't really apply to solids is what is referred to as partial pressure. So when it comes to gases, the amount of gas in a mixture can be described in multiple ways, but one way is the partial pressure. How much force exerting on the container is responsible for that particular gas? And basically what we're describing is how many collisions it's making. The more collisions it's making with the top of my solution, what in a container we would call the headspace, the more of it we can cram into the solution. There's always going to be this exchange of gas from the solution and into the headspace and vice versa. So the more of that particular gas you have in the headspace, the more you can cram in the solution. This has a couple of consequences. One, as you are undoubtedly aware, we have an increasing amount of carbon dioxide in our atmosphere, and this is resulting in an increased amount of carbon dioxide dissolved into our oceans. Roughly half of the carbon dioxide that's emitted ends up dissolving into our oceans, and that has other undesirable effects. The other effect is also with carbon dioxide and your soda pop. So if you have soda, while it's sealed, it stays nice and fizzy because that headspace is filled with pure carbon dioxide. Once you open it up, a lot of carbon dioxide exits it's replaced with air. You close it down. The total pressure doesn't change much, but the partial pressure of carbon dioxide goes down significantly because a lot of the gas in that headspace is not carbon dioxide and therefore not involved with carbon dioxide solubility in the soda. As such, your 2-liter goes flat fairly readily. Of course, the temperature thing plays a role in there too, so if you are using 2 liters for soda, I strongly encourage you, get them cold first, and then, don't open them until you need them, and then consume them rather quickly because, we all know soda goes flat pretty quick. So with that said, have a wonderful day, and I will see you in later videos.